Okay, although we had a short break, but let's continue so that we can um, end early today. Uh, so um, I guess the topic we talked about in the last lecture was a bit, you know, kind of terse, and I guess it involved lots of technical stuff. But um, uh, I guess based on your questions, I guess some of you have already, or I guess, able to follow the most important stuff. So I'm glad about that. So just a few remarks again. We take this um, uh, so the online mirror descent, and the reason is that the online mirror descent works for um, online optimization, where you have like kind of functions that are chosen adversarial way. Um, we got some questions about, I guess, like Bayesian regret for POMDP, and that relies on some stochastic assumption that I guess your environment is kind of follows some. There's a big kind of Bayesian assumption, which is nothing but the kind of the stochastic assumption on our problem setting. But uh, for the online learning problems where the losses or reward functions are generated in an adversarial way, we cannot leverage this stochastic assumption. So um, there we take the uh, uh, take this kind of online optimization algorithm, and one example is this online mirror descent algorithm. And in terms of the frequentist and Bayesian, I guess for stochastic bandit, they are relevant, but again, we are working on this adversarially generated functions, so I guess that's um, we have to kind of deal with this regret definition, which is a bit different from the stochastic regret. That's one thing. And why do we use online mirror descent, um, uh, not the mirror descent? Okay, the reason why we use the online version is that uh, we take kind of the loss functions are changing. When you apply gradient descent or mirror descent, you have to use a fixed function, but the loss functions are changing. That's why. Okay. Today, for lecture 4, we will consider a bit different problem setting, which is called the resource allocation problem. And the algorithm we use is, dual version of the online mirror descent, which is called the online dual mirror descent. And the thing that I present for today uh, uh, it's based on kind of on ICML 2020 paper, and its journal version appeared in OR 2022. I think it's a nice paper, and um, if you are, so I'm going to present the main theorem within that paper, but it talks about a bit more about that, about a bit more about the problem. If you're interested in this thing later, you can refer to the paper. Uh, so I'll introduce this problem setting, and I'll explain how this dual version of online mirror descent algorithm works for the problem. So it's related, it's based on these two papers. And okay, so the problem is the following. So we have on horizon of capital T time steps, okay? And uh, in each time step small t, we observe you know, reward function ft and resource consumption function gt, and you have an action set calligraphic xt. Okay. So it determines the reward value you incur after taking some action from this domain, and gt is resource consumption function. So there's a resource you have to consume for taking certain action, although it gives you certain reward value. And xt is an action set. Okay. It doesn't have to be a continuous, set. It can be a discrete domain, as long as I'll show you the subroutine. As long as the subroutine can be computed efficiently, you can take kind of discrete domain as well. So here, the assumption is the following. So before we start this time step t, we see the reward function and resource consumption function. And then the decision maker chooses some action xt based on this reward function and resource consumption function, okay, which generates this reward ft of xt, and it consumes this amount of resources. Okay. You can imagine on online marketing platform. Let's say you go to some online marketplace and it offers you some discounted product, okay? And you know that if you buy this item, you get some value, but the price is also written there. And you have a fixed amount of budget, okay? Or you can kind of go to let's say, online hotel booking platform, and you go to this website and you see an offer. Okay, it says that it gives you some coupon or discount option for a certain hotel in, let's say, Hawaii. Okay, and then you see this. But maybe later on you decide on you come back to the same website and it gives you a different offer. Okay. So you can, let's say you have a budget over the entire year, but then when you use your money on a certain item to accept the offer, then you get less budget for the later period, and you have to basically kind of wisely distribute your budget over kind of multiple periods. Okay, so if you consume your budget too early, then you cannot do anything over the remaining period of your time. That is your problem. And the total resource budget is T times rho. Basically, the average budget you have for each time step T is rho. And then you have this T times rho. And you are supposed to allocate this budget over this period of T. Okay. So you get to see FT and GT for now, but you don't know what to come for the future periods. So you have to be a bit wise. You can exploit the current offer, or you still have to kind of expect what's coming in the later periods. So you have to kind of take the trade-off between these two. So the goal is to maximize the cumulative reward subject to the budget restriction. Okay, but it's called the online resource allocation because you have to make this decision on taking actions without knowing the future reward and resource consumption functions. So you have to make the online decisions without seeing the future information. That is the problem. So we look at this constrained budget constraint optimization problem. So assume that this sequence of the entire sequence of reward and resource consumption functions are available to you. Then you can solve this constraint optimization problem to compute the optimum value. Okay, but this optimum value can be computed only when this entire functions are given to us. So the optimal reward is available only when this the all information is given to you already. But our algorithm has to make kind of real-time decisions based on, I guess, the available information up to now without observing the future information. Okay. Any question? Yeah, but to analyze the performance of our algorithm, we need to assume that this request, where each request consists of a reward function and resource consumption function and the action set, they are identically and independently distributed values. It comes from the same distribution over different time steps. And the regret is defined as this. So this thing is the maximum reward under budget, which is achievable only when the entire sequence of requests is available to us. But this thing is the the sum of rewards which is realized by our algorithm, and we take the expectation of these things where the expectation is taken over this request. Okay? And D is the distribution that gives you this request. So, and the goal is to design an online algorithm with small regret. It has been central problem in like modern operations research, and I guess the first one was the Edwards problem. So it basically for online platforms, it has some slots for advertisements for each kind of word and keyword or search word. It has some kind of space for different advertisements, and the online platform has to kind of allocate these different spaces over different advertisers. That's one example. And bandits with knapsacks is also a related problem. So we have so there are multiple bandits, and when we take some action, it involves not only the reward, but also the cost. That's simple. And repeated auctions with budgets, like you have a sequence of multiple auctions. Again, but if you buy some item, you have to pay some money, and then your budget is limited, but you have to allocate wisely over this course of auction procedures. And also, online stochastic matching is kind of a related problem. So you have it's related to the advertisement problem again. So you have multiple like online platforms, and you have another party of advertisers, and platforms have limited spaces, and the advertiser come in the requests come in an online fashion, and you have to allocate your space wisely. Like if you, let's say, one advertiser comes to you and then offers this money, you can take it, but another option is to just kind of reject that offer and wait for the better offer later. This is another problem. And online linear programming is another problem, including online knapsack. And assortment optimization with limited inventories. That's like so if you take so assortment optimization is that online shopping mall, you have to choose a combination or some subset of items which can be which are presented to your platform so that the customers can see this assortment, so that the maximum click-through rate is maximized. And online convex programming, online binary programming, and this problem is studied under the name of online stochastic optimization. Okay. Is there any question about the problem setting? Yeah. Okay. Okay. So I guess I was a bit inexact about listing this as an application. Are you familiar with bandwidth knapsack? Okay. So the core difference between online resource allocation and bandwidth knapsack is that so for online resource allocation, we observe the request before we make the decision. But for bandwidth knapsack, we make decision and then get to observe the reward and resource consumption. That's the core difference. So the regret definitions to analyze your performance has to be different. Okay. So for online resource allocation, you see more information. So you are able to leverage more information. So you can do better than what an algorithm for bandwidth knapsack can do. So the regret definition has to be different. Any other question? Okay, so for each time step t, we define a dual function given by this expression. Okay, so the idea behind it is as follows. Okay, so basically, again, before we decide on our action xt, we see ft and gt. Okay, we look at ft, which is about reward, and gt, which is about resource consumption. And then we decide which action xt to take. So how do we take our action xt? That will somehow depend on this ft and gt. Okay, we want to maximize the reward, But at the same time, you have to consider the resource consumption. Okay, we cannot kind of buy Lamborghini all the time. You have to kind of think about the remaining budget. Okay, so the way we think about this, we take into account this resource consumption is by taking this penalization term. Okay, so we have the reward, and if the cost is kind of too high, we have to kind of mitigate this reward by this cost function. Okay, but how do we kind of how do we combine this reward and cost function? That is given by this multiplier lambda. That is kind of like a penalization constant or coefficient. Okay, but if lambda is too high, that means that you are putting a more importance on the resource consumption. If it's set to kind of 0, which is the smallest possible value, then you don't care about the resource consumption value. Okay, so you have to kind of determine the right level of this coefficient lambda. But once you fix the this level lambda, then this is how you kind of combine the reward and resource consumption. Okay, that is the kind of like the mitigated reward after all, and your action is the one maximizing this combined reward. Okay, that's why I'm taking this dual function. So once you choose lambda, your action will be to maximize this function. So it's essentially the maximum of this combined function will be the final reward minus the lambda times your resource consumption. That's essentially why. Okay. Then we consider this kind of like this dual function. And what you can argue is that the optimal reward, which is the maximum possible reward under budget, is upper bounded by this dual expression. So this gives you a way of upper bounding this regret function. And our main task was to minimize this regret. And to minimize regret, we can minimize the upper bound given by this dual function. Let's actually prove this. If you see the proof, it gets more clear. Okay. So let's be optimal. Again, so optimal value is realized by a sequence of optimal actions x1 through x capital T. And we say that x1 star through xt star give you an optimal solution. Okay. Then because it's an optimal solution, it satisfies the long-term budget restriction. So G summation T from 1 to capital T, G small t x t star is equals T times rho. Okay, so if you multiply this by this non-negative coefficient lambda, you still have this inequality. Okay. Moreover, the optimal value is equal to summation of T from 1 to capital T, ft x t star. is less than or equal to minus lambda t gtxt star plus lambda t rho. Okay, and this is just because lambda t rho minus the left-hand side is non-negative. So I've just added a non-negative term to the right-hand side. This is fine. Okay. And here, if you look at these first two terms, you know, ft minus lambda times gt is maximized by it's less than or equal to this ft star lambda. Ft star lambda is realized at some solution maximizing this expression. So this is at least t from 1 to capital T, ft star lambda plus lambda t rho. Okay. So I just use that this thing is at least ftx t star minus lambda gtx t star. Okay. Now we define d bar lambda just to avoid the dependence on gamma. Again, gamma is a sequence of capital T requests, and then we assume that each request, these requests are IID. So what we did is we take the expectation of this new value D over multiple requests, and we divide it by capital T. So it means that like, so D expression, again, if you get back to the definition, this is somehow the summation of this dual function and T rho over capital T steps. So if you take the expectation and divide it by T, then we are basically giving, computing some average of the dual function plus lambda times rho. So this is what we do. And again, d bar lambda is, this is 1 over T expectation of summation T from 1 to capital T ft star lambda plus low lambda. Here, this expression is equal to this thing. And the reason is that request ft, gt, they are IID. So it's equivalent to just sample one request from the distribution and you get the same expression. Okay. Then for any, the non-negative lambda, we have this expression. Again, this follows from the previous lemma that opt gamma at most d lambda times gamma. We just took the expectation, and that's equal to t times d bar lambda. I think so far we just applied nothing but the weak duality result, and then we just took the expectation. Okay, here this is the maximum, the optimal reward, and d bar is a dual function, which is which combines the reward and the constraint. Okay, and then this thing is nothing but the weak duality theorem, but the expressions here are taking expectations. So we are ready to describe the algorithm, and but to guarantee the kind of bounded regret, the sublinear regret, we need to assume the following. So we have a option to take the dummy action, whose cost or resource consumption is 0. It's something like when you have an auction, there's an option of not buying anything, which doesn't require any resource consumption. Its reward can be very small, but you are guaranteed not to use any resource from your budget. So here's the algorithm. So okay, so at each time step t, you observe this request, okay, and then you compute this dual function, and you choose the solution that maximizes this this penalized function. Okay. Now you check whether this solution can be accommodated under your remaining budget. Then you take this action. If not, you choose the dummy action, which doesn't cost anything. Okay, so this is the action you choose. And then the remaining budget for the next time step will be computed by subtracting this current resource consumption from the remaining budget for the current step. Yeah. Right. So you, let's say, okay. So you apply for jobs, and then some company or some school gives you an offer, but you think that that offer is not good, and then you wait, and then you wait for the better offer. Right. Yeah. Yes. So yeah. So as long as your action is feasible under budget, then you take it. If not, you just skip it. That's, right. So your question is, instead of taking this penalized form without reflecting on this budget, your question is, why don't we just solve the constraint problem each period? Is that your question? To get, well, so somehow, okay, so here, I think that's yeah. uh, I'm getting confused. So what I want to tell you is that this thing is equal to argmax ftx minus lambda t gtx minus rho. You can take the budget parameter, like average budget parameter into your formulation, but you still get the same thing. And the reason is because rho times lambda t is independent of xt. So so this formulation, it's not considering the budget parameter, but the budget parameter is irrelevant when you take this action. If your question is about whether you may ask something like, why don't we solve ftx subject to gtx less than or equal to rho? Is that your question? Right.
There's a coupling between period.
Yeah.
It also looks like the following. And then we check the university activity actions. So why? But for me, this looks like probably this was kind of one opposed by both P1 and P1. Because one is
so you are then how do you so what is your what is your proposal? Yeah, like how do you deal with this situation instead of, so you have to you're saying you have to kind of look at the next budget? Okay. Um uh yeah. Okay, so there are kind of many things that I can, I guess, many aspects that I can discuss regarding your question. So first of all, I guess, but implementing your idea is a lot more computationally expensive, right? You have to, when you make this decision, you have to see the future outcomes. Okay, so you have to kind of plan things ahead, what happens next, and so forth. Okay, but here we are kind of like doing a greedy algorithm, right?
Which is satisfying the budget.
Yeah. I guess the only control is to run the right level of kind of balancing between the reward and resource consumption function. Okay, but still, like, this decision on lambda t doesn't really look ahead what's coming next. Okay, so when you talk about the sequential decision making, I guess you are referring to solving like MDPs or that kind of dynamic programming approach. But of course you can do that, but that's more expensive to compute. But we are doing some kind of running some greedy algorithm, but the only adaptive part is to decide the right level of lambda t, and that's actually done by this kind of online gradient descent on dual variables. But this is a lot more, right, efficient. And in fact, this is enough to guarantee a small regret. That is the thing, and the reason why this is sufficient. Okay, I guess maybe kind of after explaining that this is sufficient, you might wonder why this is efficient. The reason is that so somehow, so if you're familiar with like this functionally constrained convex optimization, we take a sequence of iterates, and then we divide, and then we take the average later, and we have to satisfy this constraint function. Maybe one solution has a large value, and the next solution may have a small value. But then if you take the average, this kind of large and small value gets kind of mitigated, and then in the end you are satisfying the constraint. And this is kind of similar. If this action is too expensive, then you kind of skip and you wait for the next one, and that's enough after you take the average. And the reason why for functionally constrained optimization, you take this kind of Lagrangian approach, and the question, and the important part is and then you run the primal dual algorithm, so you have to update your dual variable, and that's what we are doing here, basically. But this is not the primal dual algorithm. This is more about like dual descent. I don't know whether I explained. Have you taken my convex optimization class? So there were I guess there was this dual subgradient method, which is you take the Lagrangian and then you optimize this Lagrangian and get your next solution. This is basically the dual subgradient method. You take the Lagrangian and you optimize it, and that will be your solution. But the only kind of difference is that you have to have this thing. This guarantees that the resource consumption is strictly satisfied. Okay, great. Any other question? Yeah, okay, so I guess I stopped here. So again, we take this Lagrangian, okay, this is nothing but the Lagrangian, but again, the meaning is that you have the reward, and if the resource consumption is too high, you have to kind of penalize that. But then how much you penalize is dependent on this dual variable lambda t. And you greedily choose on action based on this Lagrangian. But if choosing that action violates the resource, the budget constraint, then you skip that action and wait for the better actions for the future. Okay? And you update the remaining budget. And if you see this thing, basically, this is the gradient for the function lambda. And then you take on gradient update, gradient descent on this lambda variable. Okay. And that's why it's called the online and dual mirror descent. You are applying mirror descent or gradient descent on the dual. Okay. And it's online because this GT here is changing over time. So this is the online mirror descent applied on the dual variable. That's why it's called the online dual mirror descent. Okay. So just to kind of make a connection to the previous slide, previous lecture, we applied the online mirror descent for online MDPs. There, we were not considering the resource constraint. But in this problem setting, we are looking at the reward function and also the kind of resource constraint. So the way of our approach of considering this resource constraint is by taking the Lagrangian based on this multiplying the dual variable. And that's why we are looking at this, applying this online dual mirror descent algorithm. So let's be a bit more specific. So we algorithm maintains a dual variable lambda t at each time step t. And then before we take the action for time step t, we see this reward and resource consumption function and the action set. And we look at this Lagrangian, and we greedily maximize this Lagrangian, and that gives you xt tilde. Okay, so we believe that the lambda t is a right level of balancing between these two functions, and after that, we just maximize this thing. Okay? Maybe the current level of lambda t is not correct, then we may update lambda t by running gradient descent. But for now, let's believe that lambda t is right level, then we just take the greedy action. That is the idea. And again, if the remaining budget can accommodate this action, then we take it. If not, we take the dummy action. And then we update the dual variable. And let's get back to the, this expression. So if GTXT is too large, okay, then this value will be negative. So which would be increasing this lambda t. So if you have used kind of large amount of resources, and you have to increase this kind of penalty level. But if GTXT was small, so that this lambda minus GTXT is positive, then we decrease this the dual level. So we have used a small amount of resource consumption, then we would decrease the dual. If you use a lot, then we will increase the penalty level. That is the idea. And how we adjust and kind of tune this parameter is based on running this gradient descent update. Okay. So again, by this design, it never exceeds this the budget parameter, because as soon as your greedy action supposed to kind of exceed this budget, we take the dummy action instead of this one. So it doesn't really violate the budget constraint. And again, the assumption one. What was the assumption one? The requests are IID. And when the dummy action is available, the regret is given by this expression. And when you set the step size to 1 on square root of capital T, we have this regret value. Okay. And this thing is due to learning the right value for lambda. So we are adjusting this dual variable, and this part is the error incurred by running the online mirror descent update on the dual variable. Okay. And here, this 1 over rho is the error due to kind of taking the dummy action. Okay. So again, the dummy action is the safety action. So it doesn't consume any resource consumptions, but at the same time, its reward can be small. Okay. So the optimal algorithm sees the entire sequence of reward functions and resource consumption functions, so it can plan things wisely so that it doesn't have to use the dummy action. But our algorithm can run into a kind of dangerous area where taking this kind of greedy action will violate the resource consumption function. But if you take the dummy action, its reward will be small. And this 1 on rho is due to taking that dummy action. Is there any question? Okay, let's try to prove this theorem. Okay, so we define a stopping time tau as follows. Tau to be the step as t, such that summation of t from 1 to s gt of xt is greater than t rho minus 1 and minimum. So what is it? Here, so basically, it's the right moment when you are close to violating the resource budget. Okay, so it's still smaller than or equal to t rho, but it's kind of 1 close to the current cumulative resource consumption is 1 just at most 1 away from violating the resource budget. Okay, so this is the right exact moment of kind of going beyond t rho minus 1 for resource consumption is defined as a stopping time. And so basically, up to taking this action, let's say x tau, you don't violate the resource constraint, and we assume that each resource value is bounded by 0 and 1. So remember that for any action, xt, gt of xt is at most 1. Okay, and before the stopping time, we have a kind of remaining space of greater than 1. So taking any action before the stopping time was available. So it means that so xt equals xt hat, which was defined to be the greedy action of ftx minus lambda t gtx for t divided by t less than or equal to tau. Okay, so that means that right, so ft star lambda t is equal to sup xt. It was defined as sup of ftx minus lambda t gtx, and this is equal to sup. This is equal to ftxt minus lambda t gtxt. So the reason why we introduced this notion of stopping time was to kind of avoid the dependence on the dummy action. So going beyond the stopping time, we may have to take the dummy action. And we have to take the this part for taking the dummy action into account. So up to this point, we don't care about any dummy action. We'll only look at this, we look at reward up to the stopping time, and then we will just ignore the reward after this moment. And that contributes to this error of one-on row. Okay, so we will just collect the reward up to the stopping time, and we forget about the reward afterwards, and that will result in this error of one-on row. Okay, that is the idea. You can argue that, okay, so we have ft star lambda t equals ft xt minus lambda t gt xt. So we can argue that expectation of ft xt conditional on the filtration ft minus 1. Here this is the sigma algebra defined by the first t minus 1 request. And you can argue that this is equal to d bar lambda t minus expectation of lambda t rho minus gtxt conditional on the filtration, same filtration. So the reason why I do this is that if you take zt to be summation of s from 1 to t, lambda t lambda s rho minus gs xs minus expectation of s from 1 to s from 1 to 1 t expectation of lambda s rho minus gs xs conditional on fs minus 1 and then this gt is giving rise to martingale. Okay. The reason why I'm doing this is because we have to be careful about this stopping time notion. We are kind of analyzing things up to the stopping time, but the thing is that the stopping time itself is a random variable. Okay? But if you define this martingale, then this thing implies that expectation of z tau is also 0. So gt itself is a random variable, even fixing this value t. But we are choosing this random timing tau, which itself is a random variable. So we are taking the number of terms is also a random variable, but we still get this kind of expectation being 0, and this is due to the optional stopping theorem. Okay, so once you do this, you get that expectation of t from tau lambda t rho minus gxt. Again, the expectation has to consider this randomness on lambdas and gt's, as well as the number of terms, which is equal to the stopping time. And this is equal to expectation of t from 1 to tau, expectation of lambda t rho minus gt xt, conditional on f t minus 1. Okay. So similarly, we can argue that expectation of t from 1 to tau f txt equals expectation of t from 1 to tau d bar lambda t minus expectation of t from 1 to tau lambda t rho minus gtxt. Okay, let's get to a bit about the regret analysis. So here, let's get back to this regret definition. Here regret was defined as this expected value of this gap, so optimal maximum possible reward, and the reward generated by my algorithm. And here, we can upper bound this expression. So expectation of opt gamma is equal to tau divided by t, expectation of opt gamma, plus t minus tau divided by t, expectation of opt gamma. And So here, this is at most so I need to use this expression here. So the opt gamma is upper bounded by capital T times this expected dual function. Essentially, this is tau times d bar 1은 tau times t plus 1 to capital tau lambda t plus t minus tau. Okay, and so basically, okay, I skipped this part, but here you can upper bound this thing. You can lower bound this part by you know, tau times expected d bar 1은 tau lambda t minus the same thing. So okay. Okay. So when you analyze the expectation up to some random variable time, you need to assume that you need to apply this optional stopping theorem. And we argue that this is equal to this expression. And we have this term that appeared using the convexity of d bar. And why do we care about this thing? We have this expected value of the optimal value. We can decompose this into something that up to the stopping time, and we look at the term, the thing afterward, and this thing is upper bound by something here, and then you see the same expression right here, and you can upper bound this thing as the expected reward sum plus this term that which kind of is related to the resource consumption, and that can be analyzed using that expression over there, and that's how you get the thing. And I guess we don't have much time left to kind of complete the figure, but I guess the main component again is that so we have to be careful about not violating the resource consumption constraint, and to achieve that thing, we have to take the dummy action x0 for the case when taking the greedy action violates the constraint. Okay, but so the dummy action is a bit arbitrary. So analyzing what happens in terms of this dummy action can be a bit difficult. So when we prove this regret analysis, our analysis is up to the time step when we don't really take any dummy action. Okay, we up to the first tau time steps, we only take the greedy actions and we never take the dummy action. Then we get away from analyzing what's going on in terms of the dummy action, which is a bit arbitrary. Okay, that's why we can take that xt is always our decision is always the greedy action that's related to this Lagrangian. Okay, but the issue we have to be careful about is that this time step tau is a random variable, So then we have to be kind of be careful about analyzing the expectation up to this random variable. What that can be done if you just focus on the first tau time steps where you don't take the dummy action, and when you forget about what's going on afterwards, then you pay the extra cost of 1 over rho, just because we don't look at what happens after the stopping time. And this part again, I haven't told you about this, but if you are familiar with the online gradient descent analysis, we have the thing that depends on t and the step size, and the first term has the reciprocal of this step size, and that's why we are taking this 1 on root t. This is due to the running the online gradient descent on lambda. Okay, any question? Yeah. So this is gradient descent, but if you read the paper, so I only focus on the dependence on capital T, but for some applications, you may deal with kind of different structure, like you can have a, so it really depends on the your choice of action sets. It can be like unit 4, or it can be kind of L2 box, L1 box, or probability simplex. Then depending on like the problem settings, you may or even the number of constraints. We have talked about the single constraint case, but you can have like kind of multiple resource consumption constraints. Then you may want to kind of optimize the regret in terms of the number of constraints or other parameters like the dimension of the problem. Then maybe like using the gradient descent is not the right answer. If you use mirror descent with like the entropic regularization, that might be useful for reducing the dependence on other parameters. Okay. Any other question? Okay. Thank you for sticking to the end of today's lecture. I guess I will share my lecture notes with you later today. Okay. Thank you.